Hey students, it's Miss Wicks. Today I wanted to film a quick video over our new PowerPoint, which this week is going to be looking at the parts of the brain. We're looking at neurons. So let me go ahead and do some screen share real fast. We're going to go ahead and get into that. I really love this week's topic. It's interesting. And if any of you guys are planning to go into the healthcare professions, this is definitely going to help you with those courses. If you have anatomy and physiology here at Caney Creek, if you have our medical courses, then this information will be very, very helpful for you. So today we're talking about the biological basis of behavior. And this video we're going to split up over several days. Wix is not ever trying to get you guys to watch the whole thing in one sitting. If we were in class together, this is something that I would take several days to kind of work through with my students in person. So we're going to be breaking this video up over some different days this week, and I'll include timestamps for each day so you know where to pick up, where to stop, and of course you're welcome to watch ahead if you want to, but I don't want to overwhelm anybody with excess information. So let's go ahead and get into it. Today we're talking, like I said, about the biological basis of human behavior. So we today are going to specifically be looking at neurons and neurotransmitters, and all of this information is also relevant if you're going on to AP Psych next semester. So save those notes, keep your work. We will have a digital record of all that with us working in Canvas, but all of it's going to help you next semester too. So today we're going to start with the nervous system. So imagine that you're watching an action-packed movie. As the tension mounts, your palms get sweaty and your heart beats faster. You begin shoveling popcorn into your mouth, carelessly spilling some into your lap. If someone were to ask you what you were doing in that moment, how would you respond? So there's a lot happening inside our body that influences our behaviors, sometimes with us out not even consciously being aware of it. So the nervous system is an extensive network of specialized cells that carry information to and from all of your body parts. And it's amazing how quickly these messages are relayed from the brain to the body parts and then back again. So think about it like this. If I am stepping on a tack, I need to know that so fast, I'm almost instantaneously going to get that information from my foot. That information's traveling up my spinal cord. It's being routed in my brain to the appropriate brain part that handles motor coordination, and almost instantly we can have a reflex or a response to get our foot off the tack. So it's amazing. We're talking milliseconds of turnaround time. So your nervous system is really amazing with how quickly it works and how much simultaneous parallel processing actually does occur. So the cells, we're going to be looking at neurons specifically today, and for our day, for Tuesday rather, your closing task is going to be to create a neuron. And if you're at home, we're going to be doing this out of household products. If you're here at school, we're going to draw it out. We'll have some other ways of doing it here in person. But let's talk about what it is that we would be creating. Neurons are the basic building blocks of a human nervous system. So the neurons perform three primary tasks. They receive, integrate information, and then transmit information on. And again, we're talking very, very quick turnaround, milliseconds. So it's very, very fast. The afferent neurons are sensory neurons. So they carry information from the body's tissues and sensory organs up to the brain. So if I bite my tongue, if I smell something funny, if I step on a tack, that information is coming from my senses to my brain via the afferent neurons. The efferent neurons are called the motor neurons, and this is the brain responding to that stimuli. So if I step on a tack, my afferent neurons are carrying that message to the brain, and then my efferent neurons are sending information from the brain that will tell my foot what to do in response. So when I pick my foot up to get it off the tack, that is because of the efferent neurons. Okay, so interneurons allow the nervous system to communicate internally and intervene. So again, basically, it's going to make the reflexes happen. So our body is really beautiful in terms of the reflexes that we do have thanks to these interneurons. If I need to swallow, if I need to blink, if I need to produce more tears to lubricate my eyes so my eyes don't get sticky and sting, my body takes care of that automatically with this interneuron system here. So a lot of that is also at the spinal cord. If somebody startles me, I jump back automatically, and that is just done for me. So pretty cool. So let's take a quick little tour of the neuron. Keep in mind, neurons don't touch each other. So what they're going to do, let's say we've got neurons like this, they send chemical messengers to each other called neurotransmitters, okay? Neurotransmitters are we'll get into some of the different types here very shortly, but they are excreted by one neuron to try to communicate to the next neuron down the chain. And the idea here is that all of the chemical messengers have different messages, different functions, and we'll talk about that here shortly. All of those chemical messengers, though, are absorbed by the dendrites on the next neuron. So we have the dendrites that are absorbing and sponging up all of this great chemical messenger, and then they're going to send the information to the cell body or the soma. The soma decides what to do with that information, and then the soma is going to send a message down the rest of the chain to the end of the neuron, which is the terminal button. Okay, now the terminal button is going to be the relay sensor that's sending the neurotransmitters to the next neuron down the way. So think about it like playing telephone. If I'm passing a note to somebody, that's very much like how the neurons are going to work here. So the terminal buttons are going to be what excretes the neurotransmitters to the next neuron down the line. So we're also going to see that all of this is happening super fast because of the way that the neuron is designed. When we look at the axon of a neuron, it is covered in this waxy kind of fatty coating called a myelin sheath. And the myelin sheath is almost like the plastic coating on a power cable. If you've ever had a pair of old school headphones, if you're not an iPod person, then you're in the cord life with me. But you know how it is when this cord starts to degrade and the plastic starts to chip away, the message isn't, the music isn't as clear. You start having shorts in your cable. And that's what happens with humans. This myelin sheath protects and encases the axon of the neuron, and it helps speed up the message. It also just kind of, I want to say, it maintains the integrity of the message and it maintains the speed. So later in life, some of our illnesses and issues that we have later in life, we think is in part because of the myelin sheath starting to break down. So there's some evidence that may be linked with like Parkinson's disease, for example. So this myelin sheath is to protect and encase the axon of the neuron. And then the terminal buttons are getting this message from the rest of the neuron up the way, and they're going, I need to send out dopamine. I need to send out serotonin. So the terminal buttons produce and excrete the chemicals to the next neuron down the line. Okay, and you know how it goes. Sometimes there are chemical imbalances. There's a lot of diseases. There's a lot of disorders that are linked to abnormalities with neurons. So for example, if you have depression, there's a couple of neurotransmitters that are associated with depression. If depression runs in a person's family, it may be an inherited condition where that person maybe just doesn't make enough serotonin. They don't make enough dopamine on their own. And the same way that a diabetic would take insulin to be healthy, that person would also maybe in some cases need medication to be healthy too. So again, there shouldn't be any shame or stigma to correcting neurotransmitters because that's just how a person's body is. And again, some of the disorders that we're going to talk about later in the course are temporary. Like if you're grieving a loved one who's passed away, that type of depression is probably going to lift over time. There are people, though, who have permanent chronic conditions that have to be managed the same way we would manage physical illness like diabetes or any of the others. So again, I just wanted to clarify that. So let's go ahead and skip ahead here just a wee bit. The basic parts of the neuron I mentioned, the soma is that cell body, and this is going to contain the nucleus and the chemical machinery that's most common to cells. The dendrites were the little branchy tree-like appendages that receive information from other neurons. And we also have the axon, which is the tube-like structure that carries the signal away from the soma and onto the terminal buttons. Okay? So the myelin, remember the myelin is to protect and encase the axon. It helps protect and speed up that neural impulse. And then the terminal buttons or branches are going to produce and excrete the neurotransmitter for the next neuron down the line. The synapse is the space between the neurons, okay? There's this tiny, tiny, tiny little space that the neurotransmitter has to travel across, and then that we call that space the synapse. So here's what everything is going to kind of look like labeled out. We have our cell body, which is like the life center, the life support of the cell. The dendrites absorb the neurotransmitter. The axon is passing the message down the chain. The terminal buttons or terminal branches, that's going to produce the neurotransmitter for the next neuron down the line. Okay, so real life application. Multiple sclerosis, with that condition, one of the issues that's tricky to treat is that person's myelin may actually start to break down. We can see nerve damage, and so that's something that we're still researching how to effectively treat and to correct the myelin. We want the myelin to be in place because, of course, we want that message to be preserved. When your body is, or when your brain is telling your feet to move, the myelin helps us get that information from the brain to the feet, okay? So in multiple sclerosis, the myelin sheath starts to break down, and that causes some communication breakdown between the brain and the rest of the body. So over time, that person loses some muscle control. At the cellular level, what we're going to see is that you have glial cells all around the neurons. And I always call these the housekeeper cells. They're providing support for the neurons. They're delivering nutrients to the neurons. They're producing myelin. They're flushing the waste. They prune, the dead areas away, and they also influence information processing. Sleep is very, very important for proper brain function. And, there's actually an action that happens when we're sleeping where our brain is detoxifying. I know that sounds a little goofy and not so technical when I put it that way, but if we are sleep deprived, our body doesn't have a chance to go through that cycle where we are eliminating the neurological waste. So that's happening here on a cellular level. Right? And again, what we'll see is that it's also going to influence the generation of new neurons that are happening during prenatal development. So the glial cells or the housekeeper cells, they have a very important job. All right, so that's going to be the end of day one. So that's it for Tuesday. I'm going to pick up with the information for Wednesday. So we're picking up from here on Wednesday. Now, today we're going to be talking about the neural impulse. And of course, you guys are welcome to watch the video all the way through. You don't have to break it up if you don't need to. So let's talk about the neural impulse. I'm going to skip ahead here just a wee bit. Some of this we're going to circle back to in AP. So, we'll get there. And this information helps you in AP Psych. So the resting potential is the neuron state when it's not firing a neuron, not firing a neural impulse. Yay, coffee. So this is what the neuron is doing while it's at rest. It's resting up, it's recharging. And then what we'll see is that, the action potential here is how often, how quickly the neuron can recharge and fire. So it's a very brief shift in the neuron's electrical charge that travels along the axon, okay? So again, it's kind of referring to the speed of the transmission of these messages, okay? And the same way, I'm going to skip ahead just a wee bit here, but the same way that you at your house when you're flushing the toilet, you can't continuously be flushing and jiggling the lever. The same way at your house, you have to flush and then wait for the toilet to refill before you can flush again. That's kind of how it is with neurons. When neurons fire, they have to reset before they can fire again. So, it's an all or nothing principle as well. So the absolute refractory period is the minimum rest time that the neuron needs before it can recharge and fire once again. So after an action potential, this is the minimum length of time during which another action potential can't begin. Okay, so the neuron has to basically recharge. It's just very brief, like a couple of milliseconds, and then it can, fire again. So we're not talking about a great amount of time. The threshold is the level of stimulation required to trigger a neural impulse, okay? And again, it's that all or nothing principle. I can't halfway fire a neuron. Either I have enough recharge to fire or I don't. The neuron doesn't just partially fire, okay? So skipping ahead here just a little bit, the synapse is the junction between the neurons that neurotransmitter is going to travel across. What is interesting about the synapse here is it's so small, but when we look at like the when we look at the dendrites of the next neuron, there's a lock and key principle happening. So we've got these little neurotransmitters going across, and then here on the dendrite, each of these little grooves that you see would have a specific receptor area. So this little guy right here might only accept dopamine. This one might only accept acetylcholine. This one may only want serotonin. And I want to talk about how medication works. If we have somebody who's on what we call an SSRI, or selective serotonin reuptake inhibitor, that may be anxiety medication, what's happening is that person has too much of a neurotransmitter. And the tender thing here is that we don't want to kill the neurotransmitter, because you do need it to be healthy, but you don't want so much that you're having panic attacks and anxiety issues. So the selective serotonin reuptake inhibitor is going to act here to kind of cap off certain parts of the dendrite so that you don't have too much of a good thing, okay? So if we have a patient who has schizophrenia, they may have hallucinations because they have too much of a neurotransmitter. So their medication may work on one of two areas, depending on the medication and what's going on with their body. We need blood tests to determine that, by the way. We don't just give people medicine. But that medication may work on the terminal buttons, capping off some of the terminal buttons from producing too much. If they're hallucinating because they have too much of a neurotransmitter, this medicine may work on the terminal button side, preventing it from being produced too much in excess, or it may cap off part of the dendrite. We're going to prune away or chemically deactivate some of the dendrites so that you're not absorbing too much. So again, all of these medications work differently, different brands, different dosages, and this is really where people need to have proper testing and diagnosis before they try some of these medications. They all work differently. One antidepressant is not the same as the other. And sometimes there's a little bit of trial and error period before someone finds a dosage that's correct for them. So, and again, it's just like a health condition, a physical health condition. If you had cancer, you would seek treatments, and with some of these things, if it's linked to a chemical imbalance, that's also very treatable. Okay, so as I mentioned, with the toilet analogy earlier, the neuron either has enough charge to fire or it doesn't. Just like you can't halfway sort of partially flush your toilet, same principle there. So like a neuron, the toilet has a refractory period, which is resetting. So the toilet bowl is refilling and our neuron is also going to recharge during the refractory period. Okay, so the resting potential I talked about and the all or nothing principle we mentioned as well. Either the neuron has enough juice to fire or it doesn't. It either has rested enough to fire again or it has not. So neurotransmitters, let's talk about that just a little bit. I know I've referenced the chemical messengers that they send across from neuron to neuron, but I wanted to look closely at what those specific neurotransmitters are. There are many, many neurotransmitters that our body produces, and we're only going to highlight a couple of them here in this course. But of course, if you guys are going into medicine, y'all are going to be doing a bigger deep dive into this topic in your med courses. But neurotransmitters are the chemical messengers that travel across the synapse from one neuron to the other. So this is how they play telephone. This is the messenger that one neuron is sending to the other, and this influences whether the second neuron is going to generate an action potential or not. Okay, so the excitatory effect is a neurotransmitter effect that makes it more likely that the receiving neuron will generate an action potential. Okay, so excitatory neurotransmitters, there's more likely that we're going to get action from that. The inhibitory effect is a neurotransmitter effect that makes it less likely that the receiving neuron will generate an action potential. So the second neuron, in this case, is less likely to fire, so we're calling it the red light. All right, so neurotransmitters bind to the receptors of the dendrites on the receiving neuron in a lock and key effect, just like what we talked about a second ago. The neurotransmitter is going to the dendrite, and there's a specific area that it will be received. There's only one place it can dock. So let's talk about some of that. Agonists are chemical substances that mimic or enhance the effects of a neurotransmitter on the receptor sites of the next cell. So it increases or decreases the activity of that cell depending on the effect of the original neurotransmitter. So if it wasn't excitatory or inhibitory, either way. So the example here is morphine. Morphine is a man-made chemical substance. It's traditionally used as a painkiller, but it is an endorphin agonist. Okay, so endorphins help us block pain. Endorphins I release when we work out, and that helps me with muscle fatigue. It helps us, kind of push through strains and things like that. So morphine enhances the effects of endorphins, which is also where some people abuse morphine. They're trying to get that effect. So an antagonist is going to block or reduce a cell's response to the action of the chemical or neurotransmitter. So an example of this is the acetylcholine antagonist. Okay, so an antagonist is inhibitory. Like if we have this type of poisoning, it paralyzes its victims by blocking the receptors involved in muscle movement. So it reduces in that case. We also have reuptake. Neurotransmitters in the synapse are reabsorbed through the process of reuptake. So this is applying the brakes to the neurotransmitter action, like, hey, message received, then we're going to see reuptake. So acetylcholine, I just wanted to highlight a few of the neurotransmitters here. Acetylcholine is one of the types of neurotransmitters. Acetylcholine is located in the neuromuscular junctions, and it's involved in muscle action, learning, attention, memory, autonomic arousal, like having an increased heart rate when you go up the stairs. And if the person has an abnormality in their acetylcholine levels, that is going to be implicated with Alzheimer's disease. So we're thinking now from current research, they're investigating different medications and therapies that could possibly support or replace acetylcholine because we don't produce it as well with age. So when we look at botulism, for example, Botox today, and I don't have any. I've never had any. I'm nervous about that. But Botox is going to paralyze the muscles. So it's related to this. Spider venom, So gonna also talk about dopamine. Dopamine and serotonin are what we really enjoy. Dopamine is involved in mood, it's involved in movement, it's involved in learning, attention, motivation, emotion. So right there, that's going to give us some hints about the symptoms of depression. If a person has depression, they may have sadness, of course, but a lot of times depression can be linked to abnormalities in dopamine or abnormalities in serotonin, kind of just depending on what's happening in that person's body. But this is where we see some symptoms. So it's not just sadness. That person may be really hard. It may be really hard for them to learn, to pay attention. They kind of feel like they have a little bit of a brain fog happening. Sometimes people get a little frustrated because a person with severe depression may not go out, they may not want to take showers, they may not be really motivated. And, again, there's a chemical cause there. And all of those things, it's not laziness, those are symptoms of depression. And there may be some physiological explanation there here with dopamine. Having emotional regulation, being motivated to do stuff. A lot of times we'll see side effects in school where that person just kind of loses, they don't turn in their work, they get they put their head down in class, they get really tired, they withdraw from their activities, they quit their team. So those can be some red flags, and it can be related to neurotransmitters. So Parkinson's, schizophrenia is also related to it. What we'll actually see is that sometimes some of these other disorders may be treated with other medications that also affect dopamine. So there have been times where people with Parkinson's disease are treated with antidepressants because dopamine is implicated in both disorders. So it may be one way to use that. So cocaine is an agonist that forces your body to produce dopamine. So this is really where cocaine can be an insidious drug, because your body gets used to putting, I don't need to make dopamine. Over time, if we have a person who's abused cocaine for a very, very long period of time, they become what we call a maintenance addict. If they know just enough to make dopamine, if they know what the dosage is to, have that effect, and their body will also adjust. And your body wants to be lazy. Your body doesn't want to do what it doesn't have to do. So your body will get to the point where It doesn't want to make dopamine. Like, you're going to take cocaine, so why bother? So that's an issue with rehab. A lot of times we will see that person may also need a medication to replace what the drug would normally put into play. Okay. And that's also why some people relapse really hard. They go from having this stuff artificially put into their body to cold turkey, and now my body's forgotten how to make that. And it can have some really, really terrible health effects if they're not being treated appropriately. Um, Norepinephrine is involved in mood, alertness, autonomic arousal. So sometimes people with norepinephrine abnormalities may be really tired, they're really sleepy, they're not bright and perky in the morning. It's also related to depression and bipolar disorder. Norepinephrine can be related to ADHD. And so the agonist in this case, a medication, is Adderall. What we'll actually find is that for people who have ADHD, they do have brain differences. They do have differences with neurotransmitters. And medications that are stimulants will actually help a person with ADHD focus better. So for somebody with normal brain chemistry that doesn't have ADHD, Adderall is going to pep you up, But for somebody with ADHD, if they have the right brain chemistry for this medication, this stimulant actually calms them down and helps them focus. So I love and adore many people with ADHD. Many of my family members have severe ADHD, and they describe it like their brain has 30 computer tabs open, but their medication and their therapy allows them to manage those 30 computer tabs and not get lost down the bunny trail. Okay. So again, some people grow out of the need for medicine. As you enter college, as you enter adulthood, some people grow out of that need, or they develop other skills. My husband, once he started drinking copious amounts of coffee, it acted in his system very similarly to what his ADHD medication did. So by the time he was in his early 20s, he didn't require medication, but coffee calms him down. Coffee helps him focus. So coffee has a very different impact on him than it would on me. Okay. Let's also take a peek. We're wrapping up for today, by the way. Let's also take a peek at serotonin. Serotonin is involved in sleep, alertness. Again, this is also where depression, you're noticing depression's coming up on a few of these slides. This is why if a person suspects that they may have a psychological disorder, you do not get on Dr. Google and try to find it out for yourself. And Tumblr told me to do this, that really does need to be like something you talk about with your doctor. There are different neurotransmitters associated with depression. So again, it's not a one size fits all. Here's your pill. If a person A has depression because of dopamine and person C has depression because of serotonin, they can't take the same medication. So it's really important that person go to the proper place for that treatment. Okay, so serotonin is going to appear to set an emotional tone. It's our emotional regulation. It helps us control our emotions. It's also been implicated with aggression if the person has an imbalance in serotonin. Okay. Dysregulation, we see that it is linked. If they have an imbalance in serotonin, it can be linked to depression. It can be linked to eating disorders. It can be linked to OCD. We watched a lot of the Hoarders TV show over quarantine, and we found that a lot, in almost every single case, that person required follow-up therapy. You saw great stress on their face, their behaviors when they had help cleaning out their house, because for them, it was a behavior. It can really be a disease. So again, in that case, the show provided therapy. They provided follow-up care, so that person wasn't just hey, good luck, because without care, most people who have hoarding tendencies will rebuild their hoard within the year. So it can really, really, be bad if that person doesn't seek help. So another one, GABA, is the most common inhibitory neurotransmitter. We release GABA when we're trying to sleep. GABA is what helps us not kick when we're having dreams, when we're sleeping. It inhibits movement so that we can safely sleep without flopping on our bed like a fish. It also aids in the regulation of anxiety. And so when GABA is in disarray, when we have a chemical imbalance of GABA, we see anxiety disorders, we see seizure disorders. Seizures can be very complex because sometimes people have seizures because of GABA. Sometimes people have seizures because of scar tissue or because of brain injuries that they've had. There's a lot of reasons. There's a lot of causes for seizures. So we would definitely want to see the neurologist and see what's going on there, for proper treatment. Insomnia is also part of that as well. Pharmacology, medications, substances that would interact with GABA, alcohol. Alcohol is an agonist, and the common misconception people have is that alcohol helps you sleep. Not really. What we actually find when we do sleep studies and actually research with people who are sleeping, who have had some alcohol, is that alcohol disrupts your sleep cycle. You sleep rougher, you wake up more often, you're more restless, you toss and turn more. It's not good restorative sleep. That person may go to sleep quickly, but because alcohol is a depressant, but it does disrupt the GABA, so you're not getting good restorative sleep. Okay. We will also see glutamate. I'll be quick here with this one. It's an excitatory neurotransmitter, and it's involved in learning, memory formation, and the development of the nervous system. Glutamate, if you have too much of it, like it's associated with MSG, which is a really yummy ingredient in some of your takeout food. Oh, it's so good, but it's not really good for you. A lot of people will get headaches or migraines after eating MSG because it can, the research is showing it can mess with your glutamate levels a little bit. Schizophrenia as well, if we have too much of that excitatory neurotransmitter, that's when we might see people who aren't there. Our brain is imposing hallucinations that aren't really happening. Endorphins are released when we're in pain. So endorphins are really amazing because they help us deal with pain. If we're working out, if we're in battle, we can't just stop and go, oh my, that hurts. Our body releases endorphins so that we can get to a safe place and deal with that pain. So a lot of times you'll hear on TV shows, oh, this person's in shock. That person has been injured or whatever. When you are injured, your body tries to manage pain by releasing endorphins. A lot of people who have been shot will say that they didn't immediately feel the bullets. They may have felt some burning or some numbness in that area, and the pain came online much later. And that's because of the endorphins, which will eventually wear off. If you've ever done a tough workout and then the next day you're like, oh, that hurts. I went to the CrossFit box with my sister-in-law and I'm like, oh, my thighs, how? Walking was painful the next day after those endorphins wore off. So you'll hear athletes talk about their runner's high. I have a lot of friends who jog and who love to run, and they say that they just feel a little sad and down in the dumps on days that they don't get to go out and run because they didn't get their endorphins for the day. So when we work out, that's when we release endorphins. When we eat chocolate, there's a lot of activities that can release endorphins. It's involved in pain relief and helps you respond to the stress of that moment. Okay. That's it for today, guys. Thank you so much. If you have any questions, reach out. I'm here to help. Bye.